Bismillahirrahmanirrahim. Dear students, Assalamu alaikum. Today, in this first video lecture of week 16 for the course Applied Linear Algebra, we are going to learn about eigenvalues and eigenvectors. The vector x is an eigenvector of matrix A, and lambda is an eigenvalue of matrix A if Ax is equal to lambda x. Assume that x is a non-zero vector. Eigenvalues and eigenvectors are only defined for the square matrix, that is, the number of row and number of column will be equal. So dear students, suppose A is a square matrix and x is a vector, then this vector will be the eigenvector for matrix A if there exists a scalar lambda such that Ax is equal to lambda x. It's mean that if matrix A and vector x are given, then we multiplied these two. After multiplication, if there is a common number in the matrix x, then we can write lambda x. Then in this case, this matrix, this vector x is the eigenvector of matrix A corresponding to the eigenvalue lambda. Eigenvectors are not unique. For example, if lambda is an eigenvector, so is k lambda. Zero vector is a trivial solution to the eigenvalue equation for any number lambda and is not considered as an eigenvector. Now, the definition of the eigenvector and eigenvalues. Let A be an n cross n matrix. N cross n matrix means A is a square matrix. A scalar lambda is called an eigenvalue of A if there exists a non-zero vector x in the Rn plane such that Ax is equal to lambda x. So a scalar lambda is called the eigenvalue of A if there exists a non-zero scalar vector x in the dimension Rn such that Ax is equal to lambda x. So in other words, we can say that x is the eigenvector of matrix A if there exists lambda such that Ax is equal to lambda x, then lambda will be the eigenvalue corresponding to the eigenvector x. The vector x is called an eigenvector corresponding to the lambda, and lambda is the eigenvalue. So you see over here, this is a vector x, and now you see over here, this is Ax, and x matrix Ox is the matrix, and Ax is the multiplication of vector x and matrix A. Now, computation of eigenvalues and eigenvectors. Let A be an n cross n matrix with eigenvalue lambda and corresponding eigenvector x. Thus, Ax is equal to lambda x. This equation may be written as Ax minus lambda x is equal to O. You see over here in this expression, A is the matrix, x is a vector, or sometimes we call this also a matrix, and minus lambda x is equal to O. So O is the null matrix. Now we can write suppose if you want to common the lambda, if you want to common the matrix x, so taking common the vector x, we multiplied the lambda with the identity matrix. Why we multiplied the lambda with the identity matrix? Because lambda is a scalar number. We cannot subtract a scalar number from a matrix. That's why we multiplied the identity matrix with the lambda. So we obtained in this portion, we obtained the matrix, and then we can subtract the matrix from the matrix. And now from this expression, we can obtain a minus lambda I is equal to 0 or x is equal to 0, but we cannot take x is equal to 0 because x is the non-zero eigenvector. So a minus lambda I is equal to 0. In mean identity matrix of order n. And now taking the determinant of this matrix, determinant of a minus lambda I n is equal to 0. So this is actually the characteristic equation. Solving this equation for lambda leads to all the eigenvalues of matrix A. On expanding the determinant a minus lambda I, we get a polynomial L lambda. This polynomial is called the characteristic polynomial of matrix A. The equation determinant a minus lambda I n is equal to 0 is called the characteristic equation of matrix A. From this equation we can find the eigenvalue also. And then we put the eigenvalue lambda in this equation, we can easily find the eigenvector x. Now we summarize the computational approach for determining eigenpairs. Eigenpairs mean eigenvalue and eigenvector. Eigenvalues and eigenvector is a two-step procedure. And the first procedure, to find the eigenvalues of matrix A, compute the root of the characteristic equation determining a minus lambda I n is equal to 0. From this equation, first of all, find the eigenvalues and then put the eigenvalues to find the eigenvector corresponding to an eigenvalue lambda. Compute the non-trivial solution to the homogeneous linear system a minus lambda, or sometimes if we put the lambda symbols mu, a minus mu I n into x is equal to 0. So dear students, first of all, find the eigenvalue for the matrix A using this equation determinant a minus lambda I n is equal to 0. If the order of matrix A is 3, then we put identity matrix of order 3. If the order of the matrix A is 2, then we put the identity matrix of order 2. And determinant of a minus lambda I is equal to 0. This is actually the characteristic equation. This is actually the polynomial, and this polynomial we obtain the lambda. So solve the polynomial for the value of lambda, and then using the value of lambda in this equation a minus lambda I n into x is equal to 0. Putting the value of lambda and then multiply the lambda with the identity matrix, you obtain a matrix. Then subtract the matrix from the matrix A and you will get a homogeneous system. And for this homogeneous system, we will try to find the non-trivial solution. So the non-trivial solution actually called the eigenvectors for the matrix A. For example, to find the eigenpair, to find the eigenvalue and eigenvector for this matrix A. So dear students, find the eigenvalues first of all using this equation. Determine a minus lambda I2. I2 mean identity matrix of order 2. So lambda multiplied with the identity matrix and then subtract from the matrix A, we obtain determinant of a 1 minus lambda 1 minus 2 4 minus lambda. Now the determinant of this matrix using the cross multiplication, 1 minus lambda multiplied 4 minus lambda minus minus plus 2 under 2, and after simplification we obtain lambda square minus 5 lambda plus 6. So this is actually the characteristic equation, and now from this characteristic equation we can easily find the eigenvalue. Thus the characteristic polynomial is a quadratic. You see over here, this is a quadratic, and the eigenvalues are the solution of this polynomial. We factor the quadratic to get lambda minus 3 into lambda minus 2 is equal to 0. So the eigenvalues for the matrix A is lambda is equal to 3 and lambda is equal to 2. Lambda 1 is equal to 3 and lambda 2 is equal to 3 are the two eigenvalues. Now putting lambda 1 is equal to 3 in this equation, a minus lambda I n into x is equal to 0. You see over here the eigenvalues are lambda 1 is equal to 3 and lambda 2 is equal to 2. So in second step, now we are going to find the corresponding eigenvectors for the lambda is equal to 3 and for lambda is equal to 2. Now in case number 1, for lambda is equal to 3, we have that a minus lambda I into x. This is actually the lambda value. Now multiply this lambda value with the identity matrix and then subtract from the matrix A, we obtain minus 1 minus 2 1 minus 2 1, and this is the right hand side of the system. And now we transform this matrix into row reduced echelon form. RREF means row reduced echelon form. To convert this matrix into row reduced echelon form, we obtain 1 minus 1 over 2 0 0, and you see over here at the right hand side we have 0 0 because this is a homogeneous system of linear equation. Now verify. Dear students, you can easily verify this row reduced echelon form. Thus x is equal to x1, x2 is the eigen eigenvector, and we have x1 is equal to 1 over 2 x2, so x is equal to 1 over 2 x2 and x2. This is the value of x1. So actually this system and this system, the row is the full first second row is 0, so this system has non-trivial solution. So suppose x1 minus 1 over x2 x2 is equal to 0. So now taking common x2 from this matrix, you see over here 1 over 2 and 1, and in this matrix x2 does not equal to 0. Choosing x2 is equal to 2 to conventionally get integer entries gives eigenvector x is 1 and 2. So this is the eigenvector for the matrix A corresponding to the eigenvalue lambda is equal to 3. Now for the case lambda is equal to 2, we have A minus lambda I into P. Suppose P is another eigenvector. So sometime we put capital X1 and capital X2. X1 is the eigenvector corresponding to the lambda is equal to 3, and x2 is another eigenvector corresponding to the lambda is equal to 2. Now suppose in the first case for lambda is equal to 3, x is the eigenvector whose component are x1 and x2, and now suppose p is the eigenvector for the corresponding to the eigenvalue 2. Now we write a minus 2i into p is equal to 0. And now the augmented matrix of this system you see over here. So first of all multiply 2 with the identity matrix and then subtract that matrix from the matrix A, and then take the augmented matrix minus 1 1 minus 2 2. So the row reduced echelon form of this matrix is 1 minus 1 0 0 0 0. And dear students, you can verify this system. Thus x is equal to x1 and x2. We have the eigenvector x1 is equal to x2. You see over here x1 minus x2 is equal to 0. So x1 is equal to x2. So x is equal to x2 and x2. We put x1 is equal to x2. Now taking common x2, we have the eigenvector 1 and 1, where x2 does not equal to 0. Now choosing suppose x2 is equal to 1, then we have the eigenvector 1 and 1. Dear students, note that RREF means row reduced echelon form. Now computing lambda and v, eigenvalue lambda and eigenvector v. To find the eigenvalue lambda of a matrix A, find the roots of the characteristic polynomial and determine A minus lambda I is equal to 0. Now for example, we have a matrix A 5 minus 2 6 minus 2. To find the eigenvalue and the eigenvector for this matrix, this is another example. So first of all, use the characteristics equation. Determinant of A minus lambda I is equal to 0. So this is A minus lambda I. 5 minus lambda minus 2, 6 minus 2 minus 2 lambda is equal to 0. Now expand this polynomial, we obtain lambda square minus 3 lambda plus 2 is equal to 0. And now solving this polynomial, we obtain lambda 1 is equal to 1 and lambda 2 is equal to 2. So this is the eigenvalues. And now the eigenvalues, the eigenvector corresponding to the eigenvalue 1 is 1 over 2 and 1, and another eigenvector corresponding to the eigenvalue 2 is 2 by 3 and 1. So dear students, you can easily find now the eigenvector for lambda is equal to 1 and for lambda is equal to 2 using the equation A minus lambda I into x is equal to 0. you will obtain a homogeneous equation, and then take the augmented matrix of the homogeneous equation and convert it into the reduced echelon form. You will get easily the eigenvector for a corresponding eigenvalues. Now the characteristic polynomial is a determinant of a minus lambda I is equal to 0. Suppose we have a matrix A 0 1 and 1 0. Consequently, lambda is an eigenvalue of A if and only if lambda square minus 1 is equal to 0. So that lambda 1 is equal to 1 and lambda 2 is equal to minus 1. For lambda 1 is equal to 1, a vector v1 x y is an eigenvector f 0 1 1 0 into xy is equal to xy. This yields the linear system minus x plus y is equal to 0 and x minus y is equal to 0 with solution set S is equal to t and t now taking common t, you see over here. Thus any vector of the form v1 t and t for t does not equal to 0 is an eigenvector corresponding to the eigenvalue lambda 1 is equal to 1. In a similar way, we find that any vector of the form v2 t minus t for t does not equal to 0 is an eigenvector of A corresponding to the eigenvalue lambda 2 is equal to minus 1. Specific eigenvectors of A can be found by choosing any value of t so that neither v1 nor v2 is the 0 vector. For example, letting t is equal to 1, we know that v1 is equal to 1 1 is an eigenvector corresponding to the eigenvalue lambda 1 is equal to 1, and v2 is equal to 1 minus 1 is an eigenvector corresponding to the eigenvalue lambda 2 is equal to minus 1. So dear students, in this example you see here, this is the matrix, and actually this is the identity matrix. So we can easily find the eigenvalues in the eigenvectors for this matrix A. Now another example, to find the eigenvalues and eigenvector of the matrix A minus 4, minus 6, 3 and 5. Let us first derive the characteristic polynomial of A minus lambda I. This is actually the matrix A, this is the eigenvalue, and this is the identity matrix. Because we have order 2, the matrix of the order A, the order of the matrix A is 2 cross 2 by 2. So the order of the identity matrix will be also 2 by 2. A minus lambda I. First of all, multiply lambda with the identity matrix and then subtract the matrix from this matrix A. We obtain minus 4 minus lambda, minus 6, 3, 5 minus lambda. Now by cross multiplications we obtain minus 4 minus lambda into 5 minus lambda plus 18 is equal to lambda square minus lambda minus 2. Solving this polynomial, we now solve the characteristic equation of matrix A. Solve this equation, lambda minus 2 into lambda plus 1 is equal to 0. So lambda is equal to 2 or lambda is equal to minus 1 are the eigenvalues for this matrix A. Now to find the eigenvector corresponding to the eigenvalue 2, the eigenvalues of A are 2 and minus 1. The corresponding eigenvectors are found by using these values of lambda in the equation A minus lambda I into x is equal to 0. There are many eigenvectors corresponding to each eigenvalue. For example, for lambda is equal to minus 1, we solve the equation A minus lambda I into x. Now the lambda value is minus, so A plus lambda I 1 into identity into matrix x is equal to 0. Solve this system for x. The matrix A plus 1 into identity is obtained by adding 1 to the diagonal elements of A. We get minus 3 minus 6, 3, 6 into x1 and x2 is equal to 0. So this leads to a system of equation minus 3x1 minus 6x2 is equal to 0 and 3x1 plus 6x2 is equal to 0. Thus x1 is equal to minus 2x2. The solution to this system of equations are x1 is equal to minus 2s and x2 is equal to s, where s is a scalar. Thus the eigenvectors of matrix A corresponding to lambda is equal to minus 1 are non-zero vector of the form s minus 2 and 1. So dear students, you see over here for the lambda is equal to -1, we obtain the eigenvector -2 and 1. And you see over here in this equation, in this problem, actually we have two eigenvalues, 2 and -1. So actually in this example we have two eigenvalues, lambda is equal to 2 and lambda is equal to -1. So dear students, try yourself for the next eigenvalue 2 to find the eigenvectors for the matrix A. So dear students, the process is very easy. Actually in the problem we have a square matrix A, and for the square matrix A, like you see over here, for the square matrix A we have to find the eigenvalues and the eigenvector for this square matrix A. So consider, let the eigenvalue is lambda. First of all, find the eigenvalue by using this equation, A minus lambda I. So A minus lambda I give a matrix, and then find the determinant of this matrix, and the determinant of this matrix will be equal to 0. Give a characteristic equation in which, in that equation, we obtain the lambda, and then solve this characteristic equation for the lambda. You can find easily the eigenvalues, and then put the eigenvalues in this equation, A minus lambda I into x. You will obtain a homogeneous equation, and take the augmented matrix from this homogeneous equation, and then convert the augmented matrix into row reduced echelon form. You can easily find the eigen vectors corresponding to that eigenvalues. And now this is the end of this segment. Thank you. Allah Hafiz.